Hey everybody, and welcome back to the third video in my series on the theory of thermodynamics. Today we're going to be deriving the ideal gas law. Many of you are probably familiar with from first year chemistry in university. You see this law PV. You see a couple forms: PV equals NKT, that's the thermodynamic sort of view of it, and then PV equals nRT is the chemistry view. And just for some definitions here, capital T is temperature, R is the gas constant, little n is the number of moles, K is the Boltzmann constant. We've seen that one before, and capital N is the number of particles. Also, it should be noted that capital P is now average pressure. It is not the probability. So other videos have used capital P for probability. This is the average pressure in this video. And V is the volume. So this derivation is pretty simple. So let's jump right in. Basically, you want to imagine, before I get started, this guy up here, let's just talk about this. This average energy of a system with 3 dimensions, 3 degrees of freedom, is 3/2 NKT, and I derived that in the previous video, so you will see that up there somewhere. All right, so now that we have everything we need, let's jump in. So to derive this formula, you're going to first want a sphere. That is not a great sphere, and the sphere is filled with particles that are flying around. Okay, all kinds of many particles. We know that this only works, or these equations are good for many particles. Let's throw in some axes so we kind of have a reference frame as well. So I'm just going to call this the x-axis. And then sure, let's do y and z. Bit unconventional, but it doesn't really matter. So this is our gas, and this thing has a surface, and there's an area associated with this surface that we'll call 4 pi r squared. It has a volume equal to 4/3 pi r cubed. These are just standard sort of things about a sphere. But what we want to do is we want to let's zoom in on sort of one wall. So we're going to take one wall and really blow it up. So let's see if I can do this any sensible. So here's our axes that I drew earlier. This is x, all right? And what I want to do is take an average particle. And what do I mean by average? I don't mean it's not very good. I mean that it's representative of any single particle in the system. So there's a mass, there's an average mass, and an average speed. And we're just going to let this equal m and v. So like I said, it's an average particle. It's representative of any one of these particles flying around in the system, and we're going to place it. Let me just delete this for a second or rewrite it so give myself some space. This is the x-axis. I don't need to draw it, that's fine. We place this average particle, oopsies. All right, let's try this again. Place this particle on the x-axis, okay? And the little thought experiment we're gonna do is we're gonna send this thing flying out, it'll hit the wall, and it'll come all the way back to the origin. It's an approximation, obviously, so this is m. It's going to go out with plus v, average speed, and come back with minus v. So this average particle will give us a way to sort of look at what's the force on this wall. So let's kind of define a couple things. This we are going to call, well, we know we don't need to call it anything. We know that this distance, let's use blue. This distance here is the radius of the sphere, approximately. I'm zooming in so far that let's assume edge effects don't matter. But this is the radius of the sphere. Okay, so we're going to define a delta t that is equal to it traveling and hitting the wall and then coming back to the origin. So it's going to be some distance, 2 times r, divided by some speed. Now, I really only care about a magnitude, so we're just going to call it v. So it's either plus v or minus v, but the delta t for this whole interaction is 2r over v. Okay, so now we want to get, say, the acceleration of this average particle is going to be, it's just the change in speed divided by the change in time. So the change in speed, and once again, these are magnitudes. I don't want to get picky with directions, but it's going to be the VF, sort of the magnitude of VF minus VI over delta T, which is equal to VF, it's going to be 2V, and then delta T is 2R over V. So this gives us an A average of V squared over R. Now, I don't want this to be confused with like centripetal force or anything like that. This is very much the average acceleration on an average particle traveling from the center of the sphere, hitting the wall, and coming back. So now let's ask what's the force average? It's very simple. It's MA average, which is MV squared over R. All right, we're getting somewhere. We're getting somewhere with this. So what we want to do is take. I guess I should first explain this concept. The amount of work on a gas is actually negative pressure dV. The way I like to think about this is, okay, well, if the volume, this guy here, if that shrinks and the delta is negative, then a negative times a negative is a positive, and a positive pressure. So if to shrink this volume, to actually shrink this volume takes work, it takes energy. But in this case, everything is constant, the pressure is constant, the volume is constant. We want to analyze this PV term because it's a unit of energy, and this equation shows us that it's a unit of energy. So let's work out PV. P is going to be N molecules, all right, because remember we did the average force. N molecules times the average force over the surface area. Now the surface area is 4 pi r squared, as we already talked about up here, and times the volume, which is 4 over 3 pi r cubed. Okay, so N times F average, we already defined F average. It's going to be N mv squared over R, and that R comes down here, right? So the R, this R combines with this R to make R cubed. So we get 4 pi R cubed, and then 4 over 3 pi R cubed. So what we are left with then is 1/3 NMV squared. Okay, we're getting pretty close. Thinking I can do this all on one screen. Recall that the average energy in a Newtonian system is simply going to be, let's use a different color. It's simply going to be, well, it's half mv squared, but there's n of them, so it's n times half mv squared. So what you can probably see is that this here is a multiple of that energy. So this is actually, hold on a second. Did I do something wrong? No, I don't think so. So this guy is equal to NMV squared is equal to 2 times average energy. Okay, and I hope it's clear why that is, because, well, 2 times the average energy is NMV squared. So we get 2 over 3 times the average energy. Now, what did we show in the last video? We showed that from a thermodynamic point of view, what's the average energy? The average energy is 3/2 nkt. So we pretty much got it. We got the answer. PV is equal to 2/3 average energy. 2/3, let's use a different color, times this guy, times 3/2 kt. Well, of course, that's just equal to kt. Oops, I left out an n. 3/2 nkt. 3/2 nkt. So obviously 2/3, 3/2, they cancel, and this equals nkt. So there it is. There's PV equals nkt. All right, folks. Thanks again for watching. Please like and subscribe if you like this kind of stuff. Let me know in the comments, and I will see you next time.